Via Wi-Fi, A needs to send the packets so that it reaches the router. Now, what is the principle of the MAC layer? It's the same as IP. To reach at the MAC layer destination, you create a packet with MAC destination address, the system. Here, what is the system? It's the router. Because from the local area network viewpoint, the packet is going towards the router. So it will create a packet with MAC destination address, this address here, which is the MAC address of the Wi-Fi interface of the router. Now, because it is sent via Wi-Fi to this MAC address, the Wi-Fi protocol that we've seen before will let A send to the base station. The base station will send to the router. The router receives the packet. The packet has IP destination address this. The router goes to its IP routing table, and it sees that it has to send it to this machine here. So the router will forward the IP packet on its Ethernet interface, which is given here, and will put MAC destination address, the MAC destination address of B. So this, we'll see that the MAC addresses have changed from here to here, from yellow to red. It's a different MAC destination address, but the IP destination address is always the same. If you use TCP-IP software, communication always use IP, even inside the local area network. For example, if B sends to the printer, it will do the same thing. B will send a packet to the IP address of the printer. It will not send to the MAC address. It will send to the IP address of the printer. Now, how do the two interwork exactly together? That's what is solved by what is called IP's design principle number 3, which says that communication between hosts are machines that are not routers or switches, in the same subnet should not go via a router, and between subnets uses a router. And what IP calls a subnet is, by definition, a local area network is the same, it's exactly synonym. Or it means also a collection of systems that can communicate with each other, that are able to send packets to each other using only MAC addresses. That's what we call a subnet, or that's what we call a local area network. So here there are two subnets, the Wi-Fi subnet and the Ethernet subnet here. There are two subnets, and the IP principle number 3 says that if A sends a packet to S, it should not go via the router, which could be a possibility. If I send a packet to somebody who lives in the same street as me, a postcard, I have two ways. I can walk to the house of whom I want to send it to and put the postcard into the mailbox, or I can send it to the post office, who will send it to a few houses away. Two options exist. You do what you want. You don't need to put a stamp if you use the first option. That's the main difference. IP says always use the first option. If you send a packet to the printer from B, you should not send it to the MAC address of the router, because if you do that, the router would send it back to P, but you should not do it. B should not do it, which makes sense, because which makes sense if we have Ethernet switches, which we have. So if B is able to send directly to P, there's no reason to send it here and back. You use more of the resources and you use more delay, so there's no reason to do it. In fact, it makes sense because IP was really designed as a method for interconnecting local area networks. This is why it's called internet and not net. It's not NP, it's IP. We use it today as a networking protocol, but it was designed as an inter-networking protocol, where 50 years ago, the networks were small. They existed only in research labs and universities, and there were things like this here. And computers were not PCs, right? I had a computer, but not on my office. I had a terminal to which I could connect to a computer that was in a special computer room. So a university had perhaps 10 computers, not 10,000. So the networks were local area networks. And the problem was, for example, how do I interconnect the DECnet local area network on which I was doing scientific computation? How do I interconnect it to the IBM network on which I was doing email? How do I send the result of a file that I have copied from the thing here? Well, I could copy it on a disk and copy from one to the other, or I put a router that uses IP. So that was really the networking protocol, and hence the names come from. And we see it continues to be visible because today we connect always via Wi-Fi or Ethernet. We don't connect directly to a router, which we could do. We could have a cable between my computer and the router, or I could have a Wi-Fi base station that is always a router instead and uses IP addresses instead of MAC. That's theoretically possible, but practically it does not exist today. Perhaps it will exist in 20, 50 years, we will see. I will probably not see it, but you can send me a message to heaven when that happens. A consequence of this is that a host must know on which network it is in order to apply this principle. If I send to the printer, I need to know, do I send to my default gateway or do I send directly to the printer? How do I know in which case I am? I need to know on which subnet I am. This is why we need what is called a configuration in every host, which is the subnet configuration, which is typically given by the subnet prefix. The subnet prefix, for example, is very simple at EPFL. For example, an EPFL address is, at least on the wired network, is 4 blocks of 8 bits. And the subnet prefix is always the first 24 bits. So 128, 178, 156, 128, 178, 80. In fact, the subnet ID is this, 156 or 80. All those hosts on the red subnet have 80 as the third byte. All those hosts on the yellow subnet as 156 as the third byte. So this is how we identify. And the EPFL system managers, they need to do the design here. They need to decide this part of the network, I will give 156 to it. That part, I will give 80. They need to do it. They need to count how many hosts maximum are possible. Of course, if you give a prefix, if you do this, that means the subnet ID is this. That means there's only 1 byte left to identify the system. So there are, at most, 256 devices on one subnet, not more. If there is more, this numbering plan doesn't work. So you need to do a numbering plan, and every host must know what is its subnet. In order to do that, we could do like we did in the routing table. We could give a number saying 24 is the first 24 bits here. This is what we do at EPFL. But for some reasons that are historical, we don't say 24. Instead, we say 255, 255, 255.0. That means exactly the prefix, the subnet prefix is made of 24 bits. Because it's a mask, if you take a sequence of bits, all equal to 1 in the position that identify the subnet prefix, and equal to 0 in the rest, you translate that into dotted decimal, you obtain what is called the subnet mask. It's very contorted. It was done 50 years ago. Now today we would say /24, but that's how it's done. And one lesson we learn in networking, when you do something once, the first time you do something, be very careful how you do it, because chances are it will stay forever. So the chances are you do something quick and dirty, and then it's quick, certainly, but if it's dirty, it will remain dirty forever. So changing things are very expensive, and after years, people say, oh yeah, why would I change this? Also, most people, what happens is most people did not take this course, so they have no clue of those things. They just know there is 255, 255, 255, don't know what it means and where it comes from. So at EPFL, that's the configuration we typically have. At ETH, the subnet prefix is 26 bits, which is considerably ugly or smart, depending on ugly from the viewpoint of somebody who doesn't care about computer networking and bits and bytes, and smart for somebody who loves those complexities. So, which means this is the prefix, because 192 is the binary, the decimal representation of this number, 128 plus 64, that gives 192 here. So this is what you see in your configuration here. A practical consequence is that I mentioned the fact that routing tables exist in hosts also. A host will derive its routing table automatically from its subnet mask and its IP address. For example, if I am a host here, 128.178.156.23, I must configure that my subnet mask is 24-bit long. And as a consequence of this, my operating system will automatically add into my routing table one line that says that anything that starts with 128.178.156/24 is what is called on-link, which is yet another synonym for in the same local area network or in the same subnet. So the most difficulty is the terminology here. So on-link means everything that has this IP address is on-link with me, means it's in the same subnet as me. Which implicitly means if I need to send a packet there by IP principle number 3, I should send it directly. And sending directly, it means sending to the MAC address of this destination that I have. Otherwise, by default, I send to my default router here. So when A has a packet to send to P, to the printer, it receives from the transport layer, who had received it from the application layer, the destination address. And then I look at the routing table here. Longest prefix match sends there's only the default route. Therefore, I use the default route. I have to send it to this address, which is the IP address, Wi-Fi IP address of the route. Sending to this does not mean that I put IP destination address equal to this. Remember the postcard principle. When you send a postcard to the post office, you don't put as destination address the address of the post office. You put as destination address the final destination address. But you must find a way to go to the post office. So you configure your GPS on your bicycle to go to the next mailbox or the next post office. This is what you do here. You put as destination MAC address the MAC address of the router's Wi-Fi interface here. Similarly, if B has a packet to send to the printer, it goes into its routing table that has been configured from its network mask and its IP address. And now there is a match with this that says it's on link. So when B has this packet to send, it needs to find the MAC address of the printer and send it directly to the printer here. How do I know the MAC address of the printer? Well, the MAC addresses, by principle of the MAC layer, everything should be plug and play. We should never have to configure a MAC address. We may want to if we're a hacker, we're trying to hack the system somehow. We want to break or do special things. But as a normal user, we should never see MAC addresses here. So there must be an automatic way. This automatic way is called the address resolution protocol. When B has to send a packet to P, or A also has to send a packet to P, then A has to know what is the MAC address of the router, and B has to know what is the MAC address of the printer. Well, how does it do? Well, simply by sending a broadcast. The first time B has to send a packet to P, it doesn't know the MAC address. It knows the IP address, that's done in the configuration of the printer, but the MAC address is not done there. So instead, B will send a packet that is broadcast to the entire subnetwork. There's one special MAC address with all bits equal to 1. In hexadecimal is FF everywhere. If you send a packet to this MAC address, it is sent to all machines into the system here. We see that Ethernet switches do that a lot. They do that, not a lot, but they use that to solve a number of configuration problems. At the beginning of their learning phase, when they have not yet learned all MAC addresses, they broadcast. Here it's similar. We don't know whom to send this to, so B will send a broadcast packet that will be received by the printer, by also the other computer, by this device here, and also by the router. If nobody is hacking the system, only this broadcast will be received by all systems, but the operating system will see this is an ARP packet, asking what is the IP address here. If nobody's hacking your system, there is only P that has this IP address. If nobody's hacking it, and if you did no configuration mistake, because IP addresses are configured, it's possible that two machines have the same IP address, in which case you will have big problems in your network. Probably it will not work most of the time. So normally only P has this IP address, It will receive the ARP packet, the operating system, or many times, very often, this is already offloaded in the Ethernet communication adapter, will see that this is an ARP packet and will reply by sending an ARP reply that is sent to the MAC address of B. How do I know whom to send it? Well, in the MAC packet, there is a MAC source address. So it's sent to the MAC address of B with the reply, that's me, I have this MAC address. So now B knows what is the MAC address of P. It will keep this in what is called an ARP table or ARP cache. It's called a cache because it means we keep a cache is whatever we learn on the fly, and we keep it for some time. So as long as B and P communicate, for example, if B continues to use the printer will send acknowledgements that the packets have been well received. So as long as B obtains evidence that the MAC address of P is this one, the cache is renewed. And if that happens frequently often, then the ARP will never be used again. We will use only once at the beginning. If for some reason B and P remain silent for a long period of time, the cache will be flushed. The entry will be considered to be too old, and B will need to do an ARP again. Or if you change your printer is dead, you buy a new one, but you give the same IP address to the new printer, then at the beginning it will not work. Well, B will try to send a packet, it will not work. So perhaps during 20 minutes, you are unable to use your printer. But after some time, the cache at B will decide that there was no confirmation of the MAC address of P. The cache at B will be, this entry will be deleted, and it will work again. This is why, because of things like this, sometimes we need to wait a bit until it works, after resetting things, until it works again.
Or you like already system like that?
No, it's part of the configuration of the system. Whether you can change it or not is not so obvious. I guess on an iPhone, Apple iPhone, probably it's hard to change. On the Linux PC, yes, you can change it as you want. Yes?
Possibly make addresses claim that my IP address is 128.178.80.49. Will the system be stopped by the admin?
The question is, what happens if I have another machine than P? For this one says I have the same IP address. Then it will break. It will break. So it's non-deterministic what happened, depending on which ARP reply is received first. You might send the device things here. So that's a known method of attacking a system. You insert yourself into a Wi-Fi network with a very fast and very good, you insert yourself very close to the Wi-Fi station to be sure you're more likely to receive the ARP broadcast before other things, and you reply before, and then you receive all the data.
What if others respond in a very few seconds later, and the system be locked or?
No, B will, depending on this, but I guess industrial grade systems will simply declare that this doesn't work. If you receive two ARP replies with different addresses from the same thing within a very short time, probably, I'm not sure, I have not tested that, but probably you should declare this is suspicious and stop communication. If we put all of this together, we see that IP has some configuration. An IP host must be configured with its address. That's what we've seen at the beginning. Also with its subnet mask for every interface. With its IP address of the default router. And also, as we will discuss in a few more minutes, with the IP address of several DNS servers. And in all cases, if you are in charge of designing your IP network for your smart grid, for example, you have to decide what are the subnet masks, what are the lengths, what you need, and what are the prefixes allocated to each subnet. You need to do what is called a numbering plan. It's not, nobody will do it for you. What will be done for you is automatic configuration of all the hosts. You need to have a DHCP server for that, in which you put your numbering plan. You will write the configuration file of a DHCP server and say, for example, all the yellow systems, the ones that are on Wi-Fi, they should receive this prefix. All the red things, the ones that are on Ethernet, they should receive that one. But that's your job of doing that in your DHCP server here. So much for me speaking. Let's try a few online quizzes in class. I'm using SpeakUp. So if you don't have it yet, you can either, if you have the SpeakUp app, that should work perfectly. Otherwise, you should go to, in a web browser, to this address, and you should type the number of the room that I will write on the board now. So this is the key that SpeakUp requires. So you see here, I'm trying to build my private network. I'm using 10 dot something addresses. I have an Ethernet switch here, a router, another Ethernet switch, another router, another Ethernet switch. And the question I'm asking, here are the masks are all equal to this. Here are the addresses I've given to some of the interfaces. What is a valid possible address I can give to A? I close the poll in a few seconds. Closing. You should see the result. You should see that 55% of you have chosen answer A, which is the correct answer. That is the correct answer. So why is that? Well, the prefix is given by this here, which is the clumsy way of saying the first 3 bytes, or not so clumsy here. So that means the prefix is made of the first 3 bytes of any IPv4 address. Second, we should detect where are the subnets. So the subnets correspond to systems that are connected by the same local area network technology, which is, for example, Ethernet. Now, this and that are 2 different subnets because we go from A to B, for example, via different routers. So there is 1 subnet, 2 subnet, 3 subnets here. There are 3 different subnets. And IP principle number 3 says to every subnet should correspond a different prefix. So here we see that the prefix is 10.10.2, which is consistent. The 2 interfaces, of course, I'm showing only 2 interfaces, but presumably on Ethernet, I have many, many more interfaces that I'm not showing. Here it's 10.10.1, and here it can be only 10.10.3 because I've already committed the 1 address here. So this address should start with 10.10.3. So this is valid. This is not valid. This address can be allocated only to something that would be around here, connected to this Ethernet switch. If you do this, it will not work, because when the router B sends a packet to A router will, when B sends to this address, 10.10.2, it will not go to the router. The IP principle number 2 at B says, if I have something to send to 10.10.2.22, I send directly. So I will try to find the MAC address. I will send an ARP that will be broadcast to all systems. Nobody will reply because nobody has this address if you give it here. So B will fail. It will not be able to send to A. This is how IP works. As you can see, configuration, numbering plan is important. If your numbering plan is wrong, if you give this address to that machine, it doesn't work. Communication is broken. if we put things together, let's try to analyze and do what is called a packet sniffing exercise when B sends a packet to A here. So B is on Ethernet, A is on Wi-Fi, and it has to go via the Ethernet switch, via the router, and the Wi-Fi base station here. So here's how I can put all the layers together. B is perhaps a web server that is sending data to A as a response to a query. A clicked on a web page that resulted in messages reaching the web server, and now the web server is replying. So the web server, we use the socket interface. The socket interface will be something like this. You use a function call. We say send S2. S2 is the socket that you're using, and you send a data block here. This data block will be broken into 5 chunks that fit into IP packets. That's the principle of IP packet switching. That will be passed to the network layer. The network layer will add a header, adds to the data the IP destination address of A, that's in the green header here. And now we'll send it to the router via Ethernet. In order to send it to the router, it will add an Ethernet header that contains the MAC destination address, plus also its MAC source address. So via the cable, it will reach the Ethernet switch. The Ethernet switch will analyze the MAC header. It will see the MAC destination address. It will look in its table of MAC addresses. It will see, I need to send it to the interface of the router. So it will be sent to the router. So the MAC header here is the same, has not changed. But now the destination MAC address is that of the router. So the MAC hardware says, oh, that's for me. I should copy it. I receive this packet. And then I analyze the packet. I see that's an IP packet. It has a destination address, which is not me. If it would be me, I would pass it to an application layer in me. But here, I'm not showing this. It's not me, it's A. So I look at my IP routing table. My IP routing table says, oh, it's on link with me, but on a different link, on the Wi-Fi link. So I need to send it over Wi-Fi to the MAC address of A that I need to find by saying an ARP to A, if I don't know it. And now I create a MAC header, which is a Wi-Fi header, which is quasi the same, but a bit different than the one of Ethernet. Contains in particular the MAC destination and MAC source address. It's sent over Wi-Fi. It reaches via the base station, which I don't show here. It reaches the Wi-Fi adapter of A. It sees, oh, that's for me. Removes the MAC header, analyzes the IP header. It says, oh, that's for me. It will pass it to the transport layer. The transport layer will look at the port number. The port number will say, oh, that is for this process, and I will make it available. The port number means it goes to a given socket. And then the application layer, sooner or later, hopefully, will read from the socket and will obtain the data here. So this is how all those things are put together. In terms of terminology, we have packets everywhere. The packets created by the transport layer are called segments, if it's TCP, packets at the network layer, and frame at the MAC layer, but not always. Sometimes people use the word packets also everywhere. In fact, things are a bit more complicated than what I just expressed, because what I've expressed is that a local area network is made of one Wi-Fi station or is made of one Ethernet switch. And in order to interconnect them, I interconnect them with routers, which is correct and true. Everything I'm saying is true in principle, except for mistakes and bugs. But sometimes I do approximations to make the thing easier to understand. In fact, you can interconnect local Wi-Fi areas and Ethernet systems with bridges, which are the same as Ethernet concentrators. So a bridge, an Ethernet concentrator is an example of a bridge. A bridge is an intermediate system that forwards packets based on MAC address. Intermediate system, that means it's a system that receives packets and sends them forward. It's not the destination nor the source of the packet. A router is an intermediate system. An Ethernet switch is an intermediate system. On one port, it receives a packet, it analyzes the MAC destination address, and it sends it forward. But you can do that on any kind of port. You don't need to do it just Ethernet to Ethernet. You can do it Ethernet to Wi-Fi, for example. So you can have a bridge to interconnect Wi-Fi to Wi-Fi. And worse, you can also put several bridges together, which solves a problem. You went to Migros because you had a few things at home. You have a server, disk server, media server, a printer, and a few things. And you bought a switch that has 4 ports. And now you need more. So what do? You throw away your bridge and you buy a bigger one, or you connect another one into this one, like you expect to be able to do if you buy extension cords that have multiple sockets. You can plug one in, and etc. For purely electrical things, you should not do too many of this because there are also safety problems. But for bridges, it's exactly the same. If I have one bridge that interconnects things, I can interconnect bridges together via Ethernet things, or by putting Wi-Fi interfaces if I have a bridge that has Wi-Fi interface here. And I can plug them all together and create a network here. And the principle of learning applies to this, so they will need no configuration, with a caveat. If you create a loop, like I'm showing here, I'm connecting everything to everything, so I'm creating a loop. This learning system has problem if there is a loop. Also, the broadcast has problem if I send a broadcast. Remember, at the local area network, we do broadcast. We do broadcast when we are learning. We have never seen this address before. Or we do broadcast when we do ARP, also for learning the MAC address. So the broadcast, if there are loops, then there could be problems here. Of course, the problems can be solved. The way the bridges solve the problem is to avoid loops. But they avoid it in a smart way. If you go to Migros and you buy 3 bridges, you connect them all together, you create a loop, then it will still work because the bridges are and MAC layer is supposed to be completely free of configuration. So if there would be something written on the bridge with a big exclamation mark, danger, don't create a loop, sure, somebody one day will still create a loop at Murphy's law. Anything that's possible to happen with non-zero probability will happen one day. So the things that bridges will do, they will speak to each other by sending discovery packets. So B1 will send packets to B2, B1 to B3, B3 to B2, and they will discover that there is a loop, and they will speak together and come to a consensus to disable one of the ports. If you don't configure anything, it's random. One of the ports will be disabled. Now you can say, what's the point of creating a loop and then disabling it? Well, if that's for reliability, you want to create typically a topology that has multiple links for reliability. For example, if you disable this link here, and if, so that means all traffic from A to D has to go via B3. I assume for some reason this cable is cut, or B3 hangs. You put coffee on it and it doesn't work. So this bridge doesn't work. Then the bridges, who do that every few seconds, will discover that the topology has changed. They will discover there is no loop anymore. So this link will be re-abled, and then the learning will change, and A will be able to send via D. So it's completely automatic and plug and play, and it's called the spanning tree protocol that does it. It's a fantastic protocol, but we don't have time to discuss about it, and you probably don't need to know about it. The take-home message is simply, you can make a network of bridges with a limitation, of course. The limitation is every bridge has a table, which is an exhaustive table of all the addresses in your network. If you have a few hundred, the largest bridge network that I've seen are a few thousands, you have up to a few thousand systems that works. But you cannot do that at the scale of the internet. We can have millions of entries. So that is still local area, but can be bigger than a single bridge here. For example, you could put a bridge here instead of a router between your Wi-Fi and Ethernet. In fact, that's the most usual configuration. If you have at home a small network with Wi-Fi and a bit of Ethernet, that's probably the standard configuration. That is simpler because by doing this, if you observe here, something has changed now. If you look at the IP addresses here, this is one subnet. The entire thing is one subnet. In fact, bridges are transparent from the viewpoint of IP. So when B sends a packet to A, there's no difference for B whether A is on the same Ethernet switch or not, if it's connected via bridge. There's no difference. B sends a packet to the MAC address of A, because the bridge here, there are two bridges here, the Ethernet concentrator and this one. They have tables that B, the first Ethernet concentrator, knows it should be forwarded on this port, and this one knows it should be forwarded on the Wi-Fi port here. So they are on the same local area network, even though there are two technologies here. And A or B cannot distinguish whether the other systems are on the same system or not. Cannot distinguish by, I say, with Wireshark. Wireshark is a software that we will use in the lab to look at what's inside the packets. I've shown before a few anatomy of addresses here. So we can look physically, that's very easy to do. And if you look at packets, you will see if you look at B, B is sending to A. When B sends to A, there is nothing that indicates that A is on Wi-Fi. And similarly, when A sends to B, A thinks that B is on Wi-Fi here. And that's simpler. Why is it simpler? Well, because I don't need to do a numbering plan in my system here. I just need to have one prefix for me, which is probably given by Swisscom to me. And I don't need to build a larger, more complicated network for my entire system here. For example, as I said, when A sends to P, A will look at its routing table, we'll see the destination address is on link. Therefore, I need to send to the MAC address of P. A will send a NOT packet if A doesn't know the MAC address. That will be broadcast by the Wi-Fi base station. That will be received by the bridge. When the bridge receives a broadcast, the rules of the game of a bridge is that we forward it on all the ports except the one it came, which is possible because we have a spanning tree. So that will not create a loop. There's only two bridges, so there's no problem. So the broadcast will be sent here on this port. It will reach this other Ethernet concentrator, which is a bridge. So it will forward it on all the ports. It will be received by P, and P will reply. So the ARP reply will come here. And A will send a packet to the MAC address of the printer. The bridge will send it, looking at its MAC address table. It will reach here, which will look at its MAC address table, and it will reach the print. The same. The bridge switch is the same. Historically, there are subtle differences, like the bridge is, rigorously speaking, is an intermediate system of the MAC layer. It's an intermediate system, something that handles packets by looking only at the MAC addresses. So I say we analyze the packets at point one. How can we do that? Well, if we can log into the Ethernet switch, we can start a program called Wireshark in the Ethernet switch, or we can break a cable and put a repeater that is also a splitter that will split the electronic signal so that we can pretend we will observe everything. That's what hackers will do. So whatever the mechanism, I assume I am here and I can observe all the packets that flow here. And B sends the packet to A, and we look at the destination MAC address. What should we see? Um,
From what side are we looking, from A side or B side?
so B is sending to A. That's what the arrow means.
From one, are we observing it?
So we are at one, and we see the packet as it flies here. I wait a few more seconds for the answers to improve. Voila, now it has improved, so I can close the poll. I wait until the majority is correct. Right. And the experts in that kind of tools, they say that if I give the hints that you're wrong, but I don't say who is wrong and not right, normally it gets better because the truth imposes itself with more evidence than I'm not sure it's true, at least for other domains, but here it worked. So I'm closing the poll. And the short majority says A, which is correct. Here we have a router. So we have two subnetworks, and B is sending, therefore, to its default gateway. So it's sending to the MAC address of the default gateway, which is A. Yes? Here, this box is a router, which means a router separates two subnets. Okay. Now, IP principle number 3 says, I have a packet to send to A. I need to go to my routing table. And the routing table will say, go to the router. It will not say go directly to A. I would say go directly to A if I am on the subnetwork. If I send to P, I would say that. But A is not. So I need to send to whom? To the router. So to the MAC address, which is this one. Yes? I don't know. That's the next question. That's the next quiz. What's the IP address? Of course, I've looked at the MAC address. I close the poll in a few seconds. Closing. And now the vast majority says C, which is the correct answer. So the principle of IP is we send the packet to the IP destination address in all cases. So the IP destination address is this one here. Let's continue. What's the difference with the previous case? That the box in the middle is a bridge. As a consequence, you see that the addresses have changed also. The same question. B sends to A. We observe the packet at point 1. What's the MAC destination address?
Which same as layer 2 device?
Is the bridge?
Same as layer 2 device.
I'm not sure what layer 2 device means, but the bridge is a layer 2 device. Yeah. 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 I close the poll in a few seconds. Closing. And the majority says C, which is the correct answer. Now last. Closing in a few seconds. And the majority says C, which is true. So the IP address is this one, which is the final destination address. So you see that from the application viewpoint at B, you send to this address, whether you're on the same subnet or not, is completely irrelevant from the application layer, which is a desirable property. We would not like to have software that at the application layer needs to do things differently depending on whether the destination is on the same subnet or not. That would be ugly. So another questions I could have asked is, another option I could have inserted is, there is no IP destination address, which would have been wrong, at least if we use TCP-IP software. So even if everybody is in the same subnetwork, we do use IP addresses as long as we use TCP-IP software. As I said, there is exotic software that can live without IP address, but it's really exotic. It tends to be old and no longer used or no longer developed very much. Well, let's continue. So we've done the major part in terms of difficulty, which is putting together IP and MAC. And if you've correctly answered those 4 quizzes, you have at least a good part of the notions in good place here. So this is, I would say, the major complexity and what is mostly poorly understood. If you look on the web and everything, people usually say anything randomly about those things here. So in a summary, the MAC layer is used to interconnect things, could work without IP address, was originally designed to work without IP addresses, but we still always use IP addresses everywhere. And we interconnect subnets via routers. We can think of subnet as a given MAC technology, but they can be interconnected by bridges. Now, the questions, of course, is when do I put a bridge? When do I put a router? So in this example before, why should I put a bridge or a router? The answer is you can do both. There are obvious answers. If you have 200 systems here and 200 systems there, you will probably put a router because of the broadcast, everything. So rules of the thumb, a rule of thumb is typically a subnet. You don't want to have much more than 100 devices in a subnet today, because there are broadcasts inside a subnet, and the performance might not be optimal. Question?
Can we build all of around the world just with the bridges?
Yes, you can make bridges. As I said, I've seen networks at CERN, for example, that had up to 20, 30,000 devices. It's possible. but it tends to be obsolete. The price to pay is to have bridges that are very high performance, and you avoid, what do you avoid if you put a bridge? You avoid the complexity of the numbering plan. You can put one big subnet for everyone, and in particular, if you move devices, if B moves from here to there, it will keep the same IP address, which is convenient. So it's more convenient. In small networks, you will tend to bridge things. So home networks are typically bridged. There are also limitations. There are systems and applications that work only inside a subnet. Perhaps if you use connected audio systems, that's you send your audio from your smartphone to a connected speaker or amplifier, or you use Apple's AirPlay, that works only in the same subnet, because you don't want to have your audio that's starting to leak over the internet and go everywhere, because you consume a lot of resources by doing that. So if here you want to do AirPlay from A to B, that will work. If you put a router in between, it will not work. So some systems have been designed with the hypothesis that the source and destination are in the same subnet. This is also sometimes used for security purposes. For example, if you have a very touchy application, for example, your accounting application, you expect that it's reachable only by systems that are in the same subnet as you, to avoid. So if you want to work on the software, on the accounting software, you have to physically come to places that are connected to the same subnet. This reduces the perimeter of attacks. So you can still be attacked, but you have to be physically present in the room. So there are applications that do this using a field that's present in the IP packet called time to live. Whenever a packet goes via a router, its time to live is decremented. If you put the time to live equal to 1, that means it cannot go via a router. So it's possible to force some application software to work only within a subnet, and a few applications do that. Now let's move on to another related topic of names. When we connect to systems, very often we use names instead of addresses here. So names were originally defined as human-readable synonyms for IP addresses and other things, not just IP addresses, but in our context, this is what it's used for. For example, if I use ssc.epfl.ch, if I go to this machine, it's instead of giving the IP, if I go to a web server, I typically don't give the IP address of the web server, but a name. Yeah. So names are organized in a hierarchical form, where more specific is at the beginning, more general at the end, and the last block, which you know, of course, is generic. For example, .com means anything commercial. Any name that has applied to a domain.com, and the intention is to have companies. Two-letter names are allocated to countries. So Switzerland has the CH, New Zealand has NZ. I'm not sure what this country is, but there is a country that has a GL, LI has Liechtenstein, etc. They can be reused for other purposes, but this is allocated to countries. So if you want a domain name that ends in CH, you have to ask a registrar who has received a block of names, and or who will apply for the name, and the ultimate authority is in Switzerland. For example, it's Switch in Switzerland that controls the ultimate allocation of names. For example, if you would like to say, oh, I want to take the name epfl.ch, and well, it's already taken, and if you want to dispute this, but I am EPFL, it's not okay that someone else has the name, the dispute will be in Switzerland, and that because this has been allocated to Switzerland. So this is the implication of those names here. That was the origin. Originally, the names in the internet were either 3 letters for generic, not country dependent, or country dependent in 2 letters. Then it's been open to any names. If you pay $500,000 a year, you can have your own name, whatever you want. So IBM, UBS, etc. When this was open, so a company bought this name, Saks, and created things like this to blackmail companies like Apple. So That's a true historical fact. So you can buy names. So they found a way to make name out of money, to make money out of names. For us, the interesting question is, where are the names in the packets, for example? So the first answer is they are not in the packets. When I go to a website like this one, ssc.epfl.ch, so I'm surfing the web, I find a page, and this page gives me this. I found a page or an email or something, although it's a bad idea to click on the link in an email, but I have received some information that the thing I should go to is ssc.epfl.ch. What will happen? Well, I will need to send packets to this to open a connection, probably a security association with this, as we will discuss, but I will not be able to go to this server. Sorry, the server is here. Before going there, I will need to find the IP address that corresponds to this name. And this is stored in servers that are called a DNS server. DNS is domain name system. And there are servers. Whoever owns a block of names must have a server or rent a fraction of a server in which there is a file giving all the IP addresses that correspond to all the names here. For example, here, this name is epfl.ch. So EPFL has bought from Switch the epfl.ch name. So Switch has put in its server an address that says the DNS server IP address of epfl.ch is whatever EPFL gave. This one, for example, 128.178.15.8. That's the DNS server of EPFL. That's written in the big record of Switch. And then EPFL owns all the things that end in epfl.ch. If you want such a name, you have to ask permission from the EPFL network managers, who will give it to you if you have a good reason to have such a name. And then they will write in their server the IP address of the web server that corresponds to this name. For example, ssc.epfl.ch will correspond to a given IP address, which is 51.13 here. That will be written in this server. And all servers in the world will have a way to eventually go to this server by going step by step. When we do this here, we will go to this server. We go directly to the server if we're at EPFL. That's an easy case. If I'm on the Swisscom network, I will first go to the Swisscom server. The Swisscom server will not know the answer, but the Swisscom server will know what is the IP address of the Switch server. So we'll ask the Switch server who has more information about epfl.ch. And then the Switch server will give to Swisscom the IP address of the DNS server of EPFL, and then we send our query to this DNS server of EPFL, or the Swisscom server will send. So using an application called DNS, our system will in fact go to the DNS server and send an application layer packet. IP destination address is that of the server, and there is a text, a message that says who is ssc.epfl.ch. The server will reply if the server wants to. Typically, EPFL DNS server replies only to people that are at EPFL or people who are DNS servers themselves, because we don't want to serve the entire world to avoid denial of service attacks, for example. So if it decides to reply, it will reply to me saying, how does it know it's whom to reply to? Well, my IP packet contained my IP source address. So by looking at my IP source address, I can reply to me, and the reply will contain a message saying, this is the IP address of the server. All of this is happening while I click. So when it says you click and you see it's waiting, well, it's waiting because it's finding the IP address of the server. Now that I have the IP address of the server, I can send an IP message that contains an application layer message that goes to the server, and the reply will come back in one or several messages with the images, for example, here. So you can try NS lookup on any machine here, and you will be able to simulate this. If you try NS lookup with a given name, you will have the IP address or the multiple IP addresses that correspond to this name here. So thing to remember, IP addresses, not names, are present in IP packet headers. So the internet routers, they look only at names that are contained in at IP addresses that are contained in IP headers. They never look at names. The names are probably somewhere in some of the packets. For example, if I go to a web server where I will say, I am connecting to you, and perhaps the name I'm going to is contained in the first packet, but the replies will not contain it. For example, the replies will contain the images I'm sending. One command we'll use in the lab is the ping command, which uses name. The ping command is a very useful command that is used to connect to other servers. So it sends a test message to a name or to an address, and it gives you replies. For example, on a Macintosh, I believe, yeah, this was a Macintosh, but it's the same on Windows or even on smartphones if you use the application I gave in the lecture note. I'm trying to test this address, which is in New Zealand, canterbury.ac.nz, and I'm saying send only 3 messages. So it sends 3 test messages. There are variants of pings. There is ping ICMP and ping TCP. Those are details I will skip here. And it gives the TTL, the response time, 300 milliseconds. So it says that's the time it took between me sending the reply, the server in New Zealand receiving the reply, or the machine in New Zealand receiving this reply, the reply coming back to me. 300 milliseconds is a reasonable time to go to New Zealand and back here. If I do the same thing to Zurich, I will have a reply time of a few milliseconds here. 0 packet loss means no packet was lost here. I also see the TTL. Remember, I mentioned this TTL field. When a packet is sent, it has a field that is decremented by 1 in every router. And what we see is the value when it comes, when it reaches us. Here it's 48, which means probably, I'm guessing, but I'm pretty confident that ETH puts a field of 64, that's the default value. When you send a packet, you put 64, and then you hope that there is not more than 64 routers in the path, otherwise your packet will be deleted. And here 64 minus 56 is probably 12 hops in the path between Zurich and us here, or me at home here. New Zealand, the TTL is 223. That means New Zealand, which is very remote location, they believe 64 might be too risky. There might be many, many more hops away from anybody else. They probably put a value which is larger, probably 256, 255. And when it reaches us, it's 223. So they've consumed about 30 plus hops here. Incidentally, the ping command will go to DNS, because here I said ping to this name, and when I see the reply, I have the IP address here. The IP address is not in the ping packet. Sending a test packet. What ping is doing is exactly what I showed in the previous slide. The ping software, which is an application layer software, goes first to the DNS to find what is the IP address of the destination and sends a ping packet to this. And when it prints the result, it will print nicely for me to the name and the address. So ping is another way to discover the mapping names and address, because if you ping to a name, you will have the address. Traceroute is another useful program that does a bit more. Traceroute detects all the routers between me and the destination. The way it works, it sends first a packet with TTL equal 1. The packet with TTL equal 1 will try to go to the destination, but will be deleted by the first router, because the TTL1 allows it to cross 0 router. So it will go to a router. The router will say, oh, I should forward this packet. That's my routing table says. But the TTL is 1. This packet is too old. I should discard it. And most routers, not all, but most or many routers, when they have this, they send an error message back to the source saying, I should have forwarded this packet, but I could not because the TTL is exhausted. And then the source, the traceroute software, will see this error message and will see, oh, I have an error message coming from this router. That's the first hop on the path. This is what it's doing. So it has sent a packet to New Zealand, and the first router on the path, so this is from EPFL, is called CVDistBV, exactly. That's the name that the EPFL system managers are given to the first router. And you see its address here. So I was on the I was in my office on the network 151, and this is the first error message has come from you. And then the traceroute software sends another packet with TTL equal 2. The packet forward goes towards the destination. At the second router on the path, same thing, an error message is sent, and etc. until the end here. It does not always work. Some routers don't send error messages. Routers of academic networks tend to do it. Routers of commercial networks sometimes don't want to do it because they are, well, it consumes CPU. It consumes resources to send error messages. And it's a way to attack also a router. If you want to bring a network down, you create robots. You first infect millions of systems that will start pinging, flooding with pings, with trace routes, a given destination that will force all the routers on the path to do a number of those things, which might bring the routers down. Modern routers have a way, they have a rate limitation. They send a number of error messages per minute, not more. So if there is an attack and if doing traceroute at this time, this router will not reply and you will not see the paths on the way here. You can do more. You can use Wireshark and look at a packet. For example, you will see in the lab the details. Here, I did my trace route and I looked at one of the packets sent by my machine. And here's what I see. I see it's an Ethernet packet. It is sent to this destination, which is my default router from me. And now you see name AVM audio. The names are simply extrapolated from the MAC addresses. MAC addresses should be unique in principle worldwide. How do I make sure that the MAC address of this, when it's using Wi-Fi, is different than the MAC address of this when it's also using Wi-Fi? Well, because the MAC addresses are given by blocks to providers, manufacturers. Somebody made the Wi-Fi adapter of this, and the company that made the Wi-Fi adapter received a block of MAC addresses and then gave addresses here. And the blocks are well known. They are public. So the Wireshark software knows that C80E14 is a block that has been allocated to this manufacturer. This is how it knows about it. Then it's an IP packet, this traceroute packet, that is sent. You see the time to leave 12. So it means this packet is trying to guess the 12th hop. And to whom is it sent? To this destination address here. So this is not to New Zealand. This is to ETHZ. And this is sent, this is not from EPFL now, it's from me at home here. That's my home address. You see, it's a private address. We'll talk about it a bit more. And then it's a UDP packet. That's the transport layer. It is sent to this port from this port. And then it contains essentially nothing, just contains 0, because this is simply a test packet here. Voila, this is for the names and addresses. I will conclude today's lecture, which is a bit heavy, but this is how it is, with the last ugly thing of the story, which is IPv6. So we could stop there and everything would be simple. But unfortunately, your generation will be confronted with the fact that there is IPv4 and there is IPv6. So the most widespread version of IP is IPv4, but the most recent one is IPv6. Why a new version? Because 32-bit is not enough. 32 bits means 2 to the power 32 possible address, which is 4 billions, 4 10 to the power 9. There are probably close to 10 billion people on Earth. Sooner or later, everybody will have a smartphone and a few computers, and we need several addresses per person, so that's not enough. At least if we don't use NATs, as we will discuss next week. So if you ask, for example, a block of IP addresses in Switzerland, you will not have it. A new block. The only way to obtain IP addresses that have been allocated to Switzerland is to find someone who has them already and resells them to you. So used addresses, if you want. New IPv4 addresses cannot be obtained anymore. But you can obtain IPv6 addresses. This is why IPv6 has been used, has been developed. So it extends the address field to 128 bits. So instead of 32, it multiplies the length by 4. which means that the number of possible addresses is to the power 4. Now, it's a true astronomical number. The number of possible addresses is 10 to the power 38, which is truly astronomical. It's a huge number. It's much less than the number of atoms in the universe, but still is an astronomical number. So we could put an IP address probably to every molecule on the surface of Earth with such an address space here. The good news is that it's just an addressing plan change. The rest is as before. The IP principles 1, 2, 3 that I've discussed before are exactly the same. That's the good news. The things are exactly the same. But there is still a bad news, is that for some reason that appeared to be good at that time, and in my opinion appears to be bad today, the IPv4 is incompatible with IPv6, which is a bit weird. It's like if I buy a telephone here, you might remember, you were probably already born when there was a major change of numbering plan for telephone numbers. When I arrived in Lausanne, if I would call somebody in Lausanne, I would not dial 021. I would just dial the number without the 021. Then the 021 was added. Then Zurich was 01, but it became 41 or 44. And so there was a change of numbering plan, and other countries have done more dramatic plans. In France, they've added digits but the telephones have not changed. Right? Here, well, we don't change the smartphone, but the software needs to be changed. If I have an application that has IPv6 and IPv4, they have two incompatible things in the sense that if I send an IPv6 packet to a machine that has only IPv4, the receiving thing will not be able to decode it, which makes sense. If I extend the numbering plan, I had an old number that was 6-digit, and or let's say 32-bit, I give you a number that's too large, I cannot parse it. But it's also the other way around. If I send an IPv4 packet to an IPv6 machine, it will not be understood. They are treated as different things here, which in my opinion is an error. An IPv6 machine could understand an old style packet by saying it's only 32 bits. It means that's the old fraction of the numbering plan. But the decisions were to make them distinct. Probably they were influenced by Apple. You know, when Apple creates a new operating system, all the old ones are no longer compatible, as opposed to Windows, where you can continue to have software. You can have programs that were done for Windows 95 that will continue to work in the so-called compatibility mode on Windows 11, for example. But there's a price to pay. Windows software is typically less nice and more clumsy, more error-prone as the reputation it has. So probably that's the reason. In order to make things simpler, it's incompatible. Now, that's no big deal from if you have both, which is true for all the systems in this room, are probably IPv6 and IPv4 compatible, because your latest version of Apple software or Windows software, by necessity, will run both IPv4 and IPv6 here. But it's not true of any network. You have networks that give you only IPv4 access. In fact, the EPFL Wi-Fi network has been offering IPv6 only since this year. Last year, there was no IPv6 on EPFL's Wi-Fi network, and they did it because I've been asking this for 15 years. So after 15 years of asking and the change of vice president, they eventually accepted to do it. Why do they waited so long? Not because they're stupid or bad, they're very smart, but they are just money concerned. It's a change of software on all the routers and all the base stations of EPFL. There are 1,000 base stations at EPFL Wi-Fi here. So it's like a major change. It took them 1 year to do the deployment of the new change. And as usual, when you change software, even if you do exactly the same thing as before with new software, there are still bugs and things that don't work. So it's a major change from one to the other. So in the smart grid, for example, most smart grids that I know work only with IPv4 for this reason. Why should we change? It works the way it is. Why should you change? Well, if you're a network that's emerging, for example, if in India you deploy a new cellular telephony network, you will receive only IPv6. You need 100 million new addresses, and you will receive only IPv6 addresses. So there are parts of the world where they have, because of the growth, they need to have new addresses, and they will have only IPv6 addresses. So you have IPv6 only networks. Now, in order to, those two don't work together at the network layer. You cannot, so you will need to find clumsy situations for them. Another part of the ugliness is that what happens when you move from 32 bits to 128? Well, this is an address now. That's my EPFL address on my office, on my computer in my office here. The local host is this address here. It's one. So things have been simplified because our IPv6 now, things I've learned from all the ugly things of IPv4. They've tried to make it more systematic here. But still, the address is very long. So the first thing we must learn about IPv6 addresses is how to understand them correctly. And there is a so-called compression rule. So first, we write them in hexadecimal, right? Here, I did not write in binary because writing 128 bits is truly ugly. Yeah. So it's written in hexadecimal. So when I say 2, it's not the decimal number 2, it's the hexadecimal digit 2. So you can see also F, D, E, which are, you see hexadecimal digits here. And we group them by block of 4 hexadecimal digits, which correspond to 16 bits. 4 times 4, so 16 bits. They're separated by columns. And the compression rules is that you can omit leading zeros. For example, if I have here 0A00, I can write it. I could write it, so I don't have here, but my address here, the 0620 can be put 620. I said 20, but this is wrong. I said everybody says it, so I repeat what everybody says so that you're exposed to the true reality of the world in which we live. But it's not 20. Why do I say it's not 20? Because that's hexadecimal, right? It's 2 followed by 0. So 2, the second digit means I multiply by 16. So it's 2 times 16, 32. Right? So this is 20 is 32. But of course, I don't have a computer implanted in my brain yet. So when I see 20, I think 20 and not 32. So those are the numbers, and you see they have been allocated. The numbering plan that's currently allocated is this one. You see it has been allocated in year 2001. That's why it's, but again, it's not 2001, it's 2001. And we can also, any groups of zeros can be replaced by an empty string, 2 columns, which is a convenient way of saying the loopback address. So if I send an IPv6 packet to myself, I send it to this address here. And here I see also I have an address here that has plenty of zeros in the middle. I can compress it here. Of course, there can be many times zeros in addresses. I can compress it only once here. So if you do if config on Linux or Macintoshes, IP config on Windows, you can see your address here. I see that on this machine, I have an Ethernet interface. Here I see my MAC address, which is written in hexadecimal. I have an IPv4 address with the net mask here. Interestingly here, I believe this is a Macintosh. It writes, you see that it writes the mask in hexadecimal digits. The mask is typically written in dotted decimal, but probably influenced by, I'm not sure why, it writes it in hexadecimal digits. And here I have an IPv6 address here. And similar to IPv4, there is a network mask, but for IPv6, here you say it's called prefix length 64. That means my mask is the first 64 bits. 64 means just half. That means the first 4 blocks here are just the blocks of that corresponds to my network mask here. Worse than that, in IPv6, every interface has, in addition to its normal address, like in IPv4, a thing that's very special that has been invented for IPv6, and is called the link local address. It's an address that can be used only inside the same sub-area network, the same local area network, inside the same subnet. So to understand this, we need to understand the MAC layer, which we did before. And those addresses start with FE80 here. So every interface will have such an address. And I will conclude with this here. So if I look, for example, at those different machines, a machine like this one has an IPv4 address, has an IPv6 address, and has an IPv6 linked local address. The rules of IPv6 say if A sends a packet to B, and for some reason I want to make sure I will stay in the same local area network, then a good way to do that is to use the linked local address as source and destination. You remember that Apple AirPlay or some finance software, they want to restrict access to a subnet, to a local area network. In IPv4, you have to manipulate the TTL for that. In IPv6, you can use addresses for that. That's one use of that. I believe the major use of that is that IPv6 intention is to get rid of the MAC layer. Imagine in a distant future that we don't use MAC layers anymore, but we use only the IPv6 linked layer addresses here. That would be possible, but it's a dream of the future. And in the present, where we live today, it just makes things more complicated, but it's a bit less complicated if we understand what a local area network is. Other than that, IPv6 is the same as IPv4, but it makes it a bit tough. And since we are 2 minutes late already, I thank you for your patience. Invite you to do the quiz. You can do the quiz already now for as a preparation for the lab, and then the lab.